Penn, you have moved now.
I have moved.
To State College, Pennsylvania. He's a Hubble Fellow at Penn State. Formerly, he was a postdoc at the University of Santa Cruz after he finished his PhD at the University of Arizona, where we first met. Back in the day. He works on a lot of things, but one of the things he's been leading is sort of an effort with lots of spectroscopy to understand the status of, well, really what I would call accreting black holes in very distant galaxies. We're talking about some of that work. Thanks.
Thanks, Casey. Yeah, it's a pleasure to be here. You guys have a beautiful institute. Yeah, so I'm glad I made it. My flight was canceled at the State College yesterday, so I got here in College Station at 2:30 this morning. So bear with me. You know, if I move a little fast from too much coffee, feel free to interrupt. Ask me questions. I'm going to gloss over details because I really want to focus in on the physics. So if you guys are curious about a detail, please do stop me. Ask me about it. Like Casey said, I'm now at Penn State. Let's see, is one of these a laser?
Don't put it dry.
Don't admit it.
One of them must be.
Okay.
But, we'll soon run into sleep deprivations.
I mean, I can also just point. I see a bunch of Okay. Thanks.
I think operate a phaser.
Yeah. All right. I'll try not to gesture this way too. Yeah. So I just moved to Penn State about a month ago, and I have a long list of collaborators. I'm going to show you data from the SDSS, redshift 0-ish, from Cosmos, redshift 1-ish. Actually, the background of all my slides is the Cosmos field, 2 square degrees. And I'm also going to talk about candles, which is a redshift 2-ish survey. And I'm really going to try and talk about this question: how do galaxies grow their supermassive black holes? And I have a long list of colleagues. At Santa Cruz, I worked primarily with Sandy Faber and David Koo. Now at Penn State, I'm working with Neil Brandt and Don Schneider. And at Arizona, my advisor was Chris Indy. Okay. So just a brief outline of what I'm going to tell you about. So first, I want to just set the framework for everything. I want to talk about this idea of galaxy black hole coevolution and what that means. And I'm going to give you some of the basic observations that led people to think this is a real thing. And then I'm going to talk about some of the theoretical models those observations inspired. I also want to talk in some detail about how we find AGNs, because that changes our view of this idea of galaxy and black hole coevolution. And then I'm going to dive into what kind of galaxies seem to especially promote black hole growth. And I'm going to answer this question: is there really coevolution at all? The answer, I think, is not really, which is a little bit controversial. We'll get there. Okay, so let's dive right in. So let's start off, and I'm going to tell you about what is this idea of black hole galaxy coevolution. Well, okay, 50 years ago, it's actually sort of the 50th anniversary of creating supermassive black holes. Martin Schmidt looked at these objects. They looked like little point sources, just sort of like this. They had these broad emission lines, which were redshifted, and 0.16 is pretty low redshift. But 50 years ago, this was enormous. People thought, well, what are these things? There were all kinds of ideas that people thought they might be weird ejecta flying out of our own galaxy. But eventually, it was realized that these are luminous things, very distant, and the kind of luminosity they have means they have to be accretion onto the supermassive black hole. That accretion on the supermassive black hole also leads to these very broad velocity profiles in the emission lines, because we have gas near a black hole moving at very high velocities. And originally, these things were thought to be pretty exotic and rare. They were thought to be unusual phenomena. But eventually, it was realized that every galaxy has one of these, although they aren't always on and accreting. And it was also realized that there are these nice tight relations between galaxy properties, which I'm showing on the x-axis here. We have a blue absolute luminosity, so luminosity of a galaxy. We have a velocity dispersion of the bulge component of a galaxy. And then we have another sort of mass of the galaxy as well. Yeah?
Sorry. Is it every galaxy has one, or is it every galaxy with a bulge that has one?
That's a good question.
Milky Way has one.
The Milky Way has one, and
we have a bulge.
Some bulge.
Do you think?
So what this figure here indicates is that every galaxy with a bulge has one. I'm going to show you later that I think even at high redshift, galaxies without bulges have one. I don't want to spoil my thunder.
No.
Yeah.
But 33 is kind of.
Yeah.
Doesn't have one yet, right?
Yeah. Well, so in the local universe, it's not clear. There are very low mass dwarf galaxies that do have AGNs. Henny's 210. Amy Rines wrote a paper about this galaxy. Henny's 210 is a tiny, few times 10 to the 8, 10 to the 9-ish galaxy. no bulge, none at all. It's very nearby, and it has a 10 to the 6 supermassive black hole in the center, weakly accreting. It used to be thought that only galaxies with bulges have AGNs. I'm going to show you why selection biases lead you to that conclusion, and that there may be lots more black holes than we know about. But the real key here, from this initial observation, that when you have a bulge, you have a supermassive black hole, and this observation extends over several orders of magnitude. The real idea here is that the black hole and the galaxy must somehow know about one another in a long history of growth. Because let's say we start off as a small galaxy down here with a little bulge, right? At redshift 6-ish, something like that. And then we have mergers, and we have star formation, and we have accretion onto the black hole. We grow along this line, right? And so that somehow suggests that as we grow a black hole and we go up in this axis, on the y-axis, mass of the supermassive black hole in the center, we also must go over and grow the galaxy. So somehow the two have to know about each other, right? So this is what galaxy black hole coevolution is. Somehow, as the galaxy grows, the black hole grows as well, and the black hole may actually be sort of regulating how much growth we have in the galaxy through some kind of feedback mechanism. Okay. So really these observations of the M-sigma relation, the Megorian relation, the black hole galaxy scaling relations, those are all names for the figures I just showed you. These motivated two very popular coevolution theories. So the first is this idea that galaxies and black holes grow by mergers, primarily. Okay, and this goes all the way back to Dave Sanders looking at nearby Eulergs, where he noticed that these very disturbed things that look like recent mergers tend to have very rapidly accreting AGNs. But it was really popularized through a bunch of simulations by Phil Hopkins, Tiziana Di Matteo, and Lars Rundquist's group. Okay, so this really grew in popularity about 10 years ago with all these theoretical simulations. There's a new sort of theoretical model which does the same thing, grows the bulge and the black hole in concert, called violent disk instabilities or sort of clumpy inflow. And I'll talk a little bit about that as well. And the key issue in both of these theoretical models is that you need some kind of angular momentum transfer. Okay? You need to have gas thrown inward in the galaxy. That gas thrown inward makes a bulge pretty efficiently. Also, ideally, it falls into the black hole. Okay? And both of these theoretical models also have some kind of AGN feedback to shut off star formation in most galaxies. Because otherwise, theoretical simulations have a big problem where they make too many stars. Okay, so let's first talk about mergers. And now I'm going to switch so I can show you a movie. Okay, so I'm an observer, but these simulations are so pretty that I couldn't resist showing you one. So I'm showing you a merger simulation. This is by Volker Sprengel. As you can kind of see there. You see two galaxies, two disk galaxies coming in. They are not aligned, so they're misaligned. They're coming in sort of this way. You see these huge tidal arms of gas, but also some stars. This simulation has both gas and stars. Okay, both galaxies have sort of central bulge components, but their AGN are sort of only moderately active. And you'll see that as they come together, eventually these two central components, these two supermassive black holes will merge. They'll have a quasar phase, and you'll see a big blowout coming up. So here we're coming into final coalescence. We're seeing a merger, and you sort of see the spherical shell coming out. You sort of see that? That's the quasar feedback. Okay, and that's what's shutting off star formation in the host galaxy.
Is it spherical?
It is sort of spheroidal. I don't know if it's flat. I don't know if it's a perfect spheroid. But the idea is this is part of what helps you form a nice bulge. It certainly clears all of the gas out of the bulge. So it doesn't make a lot of sense because AGN winds are not spherically symmetric. They're anisotropic. The problem is they don't actually resolve the AGN. So this is purely phenomenological.
So they're just sticking in piece of physics and stuff.
Exactly. Back to PC.
Right, that needs to be kind of spherical to clear out the gas and halt star formation.
Precisely. Yeah.
Right.
So the problem with these simulations is they don't resolve the AGN.
Right.
I'm going to come back to that. Yeah. Okay. So this is a sort of cartoon picture from a Phil Hopkins omnibus paper. This paper is something like 100 pages long. It's ridiculous. But this is a beautiful figure, and don't read the paper because it's 100 pages long, but this figure is wonderful, yeah, and I love it. Okay, so like we saw in that movie, you start out with an isolated disk. Two disks come together, they interact, they have these big tidal features. Okay, they coalesce. In the beginning, you might have a lot of obscured AGN accretion. Then you have this blowout phase with whatever kind of spherical or anisotropic blowout. The simulations don't really resolve that, so they have to throw this sort of ad hoc. And then eventually you have rapid quenching, a K plus A or post-starburst galaxy, and in the end you look like a dead elliptical. Okay? And you see this peak of star formation, sort of coinciding with AGN activity, but the AGN activity actually comes right after star formation and quenches both. Okay? Because the AGN blows out the star-forming gas, and it also blows out its own gas. Okay, so that's the idea behind this merger model, which helps you get galaxy black hole coagulation. Okay? I also want to briefly talk about this disk instability model, and I'm going to do one more switch back for this other movie. I mean, observing, I don't end up observing these pretty movies, so I wanted to show you simulations. Okay, so here what we have is a disk galaxy, which is accreting cold flows from the intergalactic medium. Okay, this is actually a picture of the gas, not the stars. And you can see these filamentary structures sort of coming in and forming clumps when they hit the disk. Those clumps are violently unstable. You will see that those clumps don't last very long. They sort of form and then dissipate immediately and tend to drive gas inward. And you can see a lot of very efficient angular momentum transport. And eventually this, we sort of get a pretty sort of normal, stable-looking spiral army kind of disk with a number of these clumps. And these clumps don't last very long again. They are violently unstable. That's the idea. And they rapidly fall inward, and they promote bulge growth, and they promote AGN activity. Okay. Okay, and a sort of stop motion view of what we just saw. You see this gas, you see cold flows coming in along filaments. These are, these little clumps you see are not actually individual galaxies. The clumps form in situ within the galaxy rather than ex situ. Ex situ clumps are really just mergers, right? If you have a clump outside the galaxy and then it falls in, that's really just a minor or major merger. And the clumps are unstable. The stars may look like this, while the gas looks sort of like that. And the inflowing clumps might feel an AGN. But I really want to point out that neither of these simulations actually resolve accretion under the supermassive black hole. Similarly, they don't resolve any kind of feedback coming off of an accreted black hole. So they sort of make phenomenological sense, but we don't know if they're real. We don't know if they're true. But they're all motivated by these sort of bulge black hole relations. Okay, so now I just want to talk a little bit about how we find AGNs and look at their hosts. Okay. So I'm going to jump through a bunch of different methods. I'm going to tell you what's wrong with each of them. And then I'm going to talk about a new method, which I think is pretty promising for learning a little bit more about AGN and their host galaxies. Okay, so I'm going to first start talking about broad emission lines, which are good for finding the most luminous and unobscured AGNs, also called quasars. Okay, these things that Martin Schmidt found back in 1963. I'm going to talk about X-ray selection and the mass biases that come with it. And I'm going to talk about BPT diagnostics, narrow emission line ratios, and again, the mass bias that sort of comes along with that. So let's start off with broadline AGN. This is sort of the classical picture of what an accreting supermassive black hole looks like, but this really only represents the most luminous supermassive black holes. You see a very blue and UV bright continuum. You see these very broad emission lines, particularly these highly ionized permitted lines, carbon 4, or even partially forbidden lines like carbon 3, magnesium 2, so triply ionized carbon, doubly ionized carbon, singly ionized magnesium, doubly ionized oxygen 3, of course. You can detect these broad emission lines, and these kind of systems, very luminous, unobscured, tend to outshine their host galaxies. So right away you can see that's a problem if we want to learn about how black holes and their galaxies grow together, because we can't learn anything about the host galaxies of these systems, because they totally outshine their host galaxies. And it becomes very tricky for decomposing the central point source quasar emission and the galaxy emission. Okay, so X-ray selection is one of the more efficient ways to find one of the most efficient ways to find AGN. You have very little contribution from contaminants, if you will, because AGNs are very luminous in the X-rays. You see that here in this plot of nu, F nu versus nu. So X-rays are all the way out here. Inactive galaxies tend to peak around here. This is like a K-band, 2 microns. The problem is X-rays miss obscured AGNs, okay, which tend to have their X-rays are very easily to extinct if you have gas and dust, and that ends up being reprocessed out here in the far infrared. In addition, as your AGN gets weaker and weaker, it falls below typical limits for even the deepest X-ray surveys performed by Chandra in these deep fields of Cosmos or Campbell's. So X-rays are good, but they only find sort of moderate luminosity and unobscured AGNs. And the other problem with X-rays,
Where are the X-rays coming from?
what are they coming from? They're coming from inverse Compton emission and Bremsstrahlung. So they're coming from a corona sitting near the supermassive black hole.
They're not shocks.
No, they're not shocks. There is potentially some X-ray emission coming from the radiojet shock material in there, but it is not dominant, at least where Chandra operates. Yeah. Eventually, as you go to something like 250 keV, you also have pair annihilation and things like that for two X-rays. But we don't really have telescopes that operate at this yeah. Okay, so another problem with X-ray selection is that there's a mass bias. So when people started looking at these X-ray selected surveys, they said, oh, look at this. If we look at the AGN fraction with stellar mass, we see these steeply increasing fractions. And again, this lends to the idea that only massive galaxies, which tend to have bulges, tend to support AGN accretion. Okay? But both in this paper from Neil Brandt's group and by James Aird, they noted that, hold on here, this is actually just a selection effect. It actually turns out to be much easier if you look at the probability of finding an AGN at a given X-ray luminosity, both top and bottom, at different redshifts. If you look at these probabilities of finding AGN, it actually increases a ton as you go to higher mass. Okay? And the big idea here is that if you imagine that every AGN has, an AGN in any galaxy has the same distribution of accretion rates. We usually represent accretion rate by this unitless Eddington ratio parameter. Okay? And Eddington ratio is basically just AGN luminosity divided by mass. Mass of the AGN, or because of the M-sigma relations, mass of the galaxy. Okay, so just AGN luminosity divided by mass of the galaxy. You can see that you can detect maybe sort of moderate accretion rate AGNs at high mass galaxies, because moderate accretion rate, high luminosity, high mass, right? But as you go to lower mass galaxies, to stay at the same accretion rate, your luminosity is dropping, and you eventually are not able to detect that kind of system. Right? You're only able to detect the highest accretion rate things, which have a high luminosity and a moderate mass. Okay, so there's this, I mean, you can, if that sort of hand-wavy description doesn't make sense, just look at these diagrams, because they're showing the same thing graphically. X-rays are biased towards finding AGNs only in high-mass galaxies. Okay, so if you want to learn about what kind of galaxies AGN live in, this is a problem. Another way to find AGNs, and this method is actually quite nice for finding AGNs, even beyond the limits of X-ray surveys. You can look at the narrow emission lines, okay, which come out of an AGN. This is also convenient because these narrow emission lines come from far away from the AGN, so they're not very susceptible to dust, which is nearby. So you can see obscure things, you can see fainter and more weakly accreting AGNs. So if you look at the narrow emission line spectrum of a Seyfert AGN, it's just a sort of weak kind of AGN, you see that O3, this forbidden line, ionization forbidden line, is quite luminous, quite bright, whereas H beta is quite weak. Okay? Same thing, N2, another partially ionized forbidden line. Yeah, so I've labeled it right here. N2 is also quite bright compared to H alpha. And if you look at an H2 region, okay, which is just star formation, you can see that O3 and H beta are comparable, and H alpha is quite a bit brighter than N2. Okay? I can give you a zoom in of this, but you get the picture, especially when you see these line ratio diagnostic diagrams. So here we have the ratio of that O3 line to the H beta line on the y-axis, and we have that ratio of the N2 to H alpha. Basically, we've got a ratio of a highly ionized forbidden line to a recombination line. Okay? AGNs tend to have high ratios of both. They sit up here, they're these blue points. Star-forming galaxies sort of follow this sequence right here. Okay? So this is called the BPT, the Baldwin, Phillips, and Turlovich 1951 diagnostic. It's one way to distinguish the hard ionization coming from the central AGN from the sort of softer ionization in a normal star-forming region. So this is another way to find AGN. But again, we have this problem where it's much easier to find AGN by narrow emission lines in the highest mass and also quiescent galaxies. And you see that in these two panels. This is actually work that I did with a student, a high school student, this past summer. Very clever student. So the AGN fraction appears to be highest as we go to high masses and as we go to red galaxies, because these galaxies have no emission lines from star formation. Okay? However, when we get to the blue clouds, lower mass and particularly blue galaxies, you can see that these H2 region lines, we're going to add them on top of the AGN lines. As we increase star formation, we just dilute those AGN lines. And in a red galaxy which has no emission lines of its own, it might be easy to find an AGN up here. But then as we have star formation, we sort of move towards the star forming track as we dilute those AGN emission lines. And that's what you see. This is really just a bias. It becomes very difficult to find AGN using these line ratios in star forming galaxies and in low mass galaxies. So again, this is a big problem. I want to know what kind of galaxies most promote AGN growth, but I'm biased against certain types of galaxies. Okay? So I think I think I'm not going to talk about this, but if you're curious about these line ratio methods at high Z, you can ask me questions at the end of the talk. I think I'll just skip through this now. I think a promising new method for finding AGN, which is less susceptible to these same biases, is actually using spatially resolved emission line ratios. Okay, I think this has become really interesting because, in particular, the HST width regrism, which gives you spatially resolved, HST spatial resolution, resolved spectroscopy. Okay? And so you can actually look at the nuclear emission line ratio of a galaxy compared to the extended emission line ratio of a galaxy. Is it possible to turn the lights on?
No. Yeah.
Just so you can see this a little more clearly. Sorry to be. Oh, perfect. Yeah, okay, so you can see, you can actually measure a nuclear emission line ratio. This is actually H beta. This is O3, so this is, highly ionized forbidden line compared to a recombination line. And you can compare that to the same line ratio in the outskirts. Okay, this is actually stacked data, so you can see this effect a little more clearly. But I think in the future with JWST, which is going to have a very powerful infrared IFU, I think actually the future of the Hubble, of HEDDEX, we'll just say that, the Hubble Everly Telescope, with its IFUs, and I think a lot of large ground telescopes, 10-meter class, are going to be building new IFUs. Well, certainly the TMT and the GMT. You guys are GMT, is that right? Yeah. So the GMT, will also be doing this. Thanks. Okay. And I think having this ability to spatially resolve emission lines is also.
Right, but I get it from there.
Yeah, yeah.
Well, I think this is fine.
No, you got the.
Keep talking.
Okay, I think you can learn a lot about a galaxy properties from doing this. You can really separate the interior region, which is less diluted from star formation, compared to the external regions, which are all just star formation. And you can really look at these line ratio gradients. And it becomes especially cool when you have these unusual looking sort of chain galaxies at high redshift. You can see really unusual structure in both their emission lines and also in their emission line ratio gradients. And this thing tends to have the highest ratios in the center, whereas this sort of off-nuclear clump looks more like star formation, or even possibly shocks. Because in sulfur 2 range alpha, it's higher compared to O3 over beta. Anyway, the point is this is a very interesting way to resolve AGN apart from their host galaxies, and it's much less sensitive to star formation dilution. And it also helps you not worry about unusual ionization in star-forming regions, shocks, things like this, and really, sort of efficiently and reliably select AGN, even going high redshift. Okay, so given all those ways of finding AGN, let's combine all those methods, and what kind of galaxies do they say? So I'm going to step through a whole bunch of different surveys that I've worked on and that others have worked on, finding AGN in different ways, seeing what kind of host galaxies they lie in, and then I'm going to combine all the data into I'm going to combine all the data into my sort of cartoon model for what galaxies most host AGN. Okay, so part of the reason that this theoretical merger simulation model became so popular is because, again, back in 1988, Dave Sanders said, oh, look, we have all these highly disturbed ULIRCs, which are certainly recent galaxy mergers, okay? And they tend to have rapidly accreting, highly obscured AGN, okay? And you see the same kind of things when you look in hard X-rays. You see, again, very disturbed galaxies hosting rapidly accreting AGNs. And you see the same kind of thing hosting a class of AGNs called broad absorption line quasars, which are basically highly accreting and highly obscured, moderately obscured luminous AGNs. So the key thing is all of these different categories of AGNs are extremely luminous, okay, and they are obscured. And they all tend to sit in mergers, okay? This part wasn't quite known as these were first found. You know, as these were first found, people said, "Oh, mergers support AGNs. That's great. You know, this theoretical simulation works." But then when people looked at higher redshift using X-ray selection, they did not find any kind of merger preference. Okay. For example, at redshift 2-ish, if you compare mass-matched control galaxies, blue points, with AGN host galaxies, red points, even though there are a lot of mergers, depending on how you quantify them, the AGN are not more likely to be in mergers than those mass-matched dynamic galaxies. Okay? So, you know, as people looked at more distant galaxies using X-ray selection, they tended to see, hold on here, and the mass matching, which is great, because again, you know, X-ray selection has a bias. They tend to see that there's no preference for mergers killing AGN. So what's going on here? You know, why do all these redshift 0 things have mergers? Well, these guys don't. Well, it's just because these are all extremely luminous and obscured AGNs. And these are much more moderate luminosity, sort of peak of the luminosity function. I'll call them normal AGNs. Again, peak of the luminosity function. Certainly, these are the most numerous kinds of AGNs. And I will also argue that they're probably more than 50% in terms of even integrated accretion rate over the cosmic history. Okay. What about violent disk instabilities? You know, do we observe that? Do we observe violent disk instabilities as sufficiently fueling AGNs? Well, Frederic Bourneau argued that indeed he did see AGNs in these clumpy disk galaxies. Well, I've been looking at the same thing in redshift 2 and some work in PrEP. So I have mass-matched samples from candles. Here you see some clumpy galaxies. And I thought, let's use these emission line ratios and see if we can find AGNs. So, you know, mass matching, we see clumpy galaxies, we see smooth galaxies, we see intermediate galaxies. Intermediate, you know, just between smooth and clumpy. Okay? And you see no real difference between the 3 categories. Okay? But, you know, I'm not totally sure about this method of using emission line ratios. I've also had to replace one of the line ratios with stellar mass. I don't want to talk about that because a better way to do it is using these spatially resolved emission line ratios, I think. So what happens when I do that? Well, it turns out that the smooth galaxies and also the intermediate galaxies, they look like real AGN. You know, the nuclear region looks more AGN-like than the extended region. Okay, so I think there's really an AGN here. For the clumpy galaxies, the nuclear region and the extended region ratios look the same. So these clumpy galaxies are probably instead dominated by shocks, by high ionization, high electron densities, high electron temperatures, things like this. And they don't really host AGN at all, right? So I would actually argue that clumpy galaxies may be less likely to host AGN. So I don't think this violent disk instability picture works for making rapidly accreting supermassive black holes. Okay? Instead, I think these sort of normal, the bulk by number,
I'm just curious going back to the clumpy thing, but
yeah.
I mean, the clumpy galaxies and the way you're selecting them match up with what the simulation will show. Because if you get a couple clumps at a time in a simulated galaxy,
Yes.
you may or may not be able to discern. So if you also get clumpy, it could be.
Absolutely. That's a really good question. So you know this, but for everybody else, when it comes to how these clumpy galaxies, smooth galaxies, intermediate galaxies are selected, and candles, we use these visual classifications. Okay? And so we actually have a grid of what we call clumpiness, where you just count clumps, and then we have a grid of patchiness, where the galaxy, you know, well, looks patchy, right? We've taken lots of merger simulations, and what we call it candlizing them. We make them look like observations. Okay, so we take snapshots of theoretical simulations, we do radiative transfer, we do a dust extinction, and it turns out that a lot of the clumps that you see very clearly become extincted, and galaxies tend to look patchy. So when I'm calling these clumpy, they're actually sort of a mix of clumpy and patchy, which matches the clumpy disk, the violent disk instability.
Clumpy and patchy.
Exactly. Yeah, so I use a sort of, if you think about clumpiness, patchiness, I sort of select on a diagonal. So it has to be both, it has to be at least a little clumpy and lots of patchy, or at least a little patchy and lots of clumpy, if that makes any sense. Yeah.
You're doing the same way for both, so it doesn't make sense.
That's right.
But I would be curious to see, you know, strictly clumpy or strictly
Yeah.
patchy, if you see any.
Yes, that's one reason this is still in prep, because that's something I very much want to do. Yeah, it's a very good point.
I like the smooth. I mean, that's really.
Yeah.
Anyway, let's look
Yeah,
at it later on
I
in the session.
really think this is a promising way to
Yeah.
look at AGN fractions, and it tells you very different things than when you just look at the basic line ratios. Okay, so normal sort of L stars AGN, accreting supermassive black holes. Where do they lie? They don't really lie in mergers. They don't really lie in things with violent disk instabilities. Well, let's just look at them on a color mass diagram. Okay, so rest frame U minus Z color from SCSS galaxies, absolute luminosity, stellar mass. The AGNs tend to lie down here. So we see no preference for stellar mass after we're careful with selection biases. Okay, they're sort of distributed, all over the place in stellar mass. But we do see that they don't sit up here in the red sequence. Okay, so this is the red sequence, this is the blue cloud. At this particular redshift range, we lose some blue cloud galaxies, so that's sort of why you don't see a very clear, high density region for the blue cloud with the gap for the green dot. But anyway, they tend to lie in the bluest galaxies of any given mass. Okay? Yes.
So can you explain what are contours and what are they?
Oh yeah. Sorry, the contours are inactive galaxies. Okay, so this is sort of the background galaxy population. Red sequence, blue cloud. Red sequence is quiescent, blue cloud is starform. Okay. Yeah. Sorry, I didn't say that. And these shaded boxes just tell you the AGN fraction. Okay. And I selected these AGNs. They're basically type 1 Seiferts if you're an AGN funded. They're sort of moderate luminosity, but they have broad lines. So they are unobscured, but they're not the most luminous.
This is all Sloan.
This is all Sloan. The reason I couldn't look at the most luminous things is because I had to take out the point source and study the galaxy behind it. We did a lot of tests of this, and we think we did a good job. Yeah. Okay. So these sort of normal, moderate luminosity AGNs tend to lie just in the most star-forming galaxies of a given mass. No real preference for stellar mass, but they do prefer blue galaxies. And it actually turns out that the more luminous the broadline AGN, the bluer the host galaxy. Okay, I'm calling this an offsetting galaxy color because I basically just control for stellar mass. Okay, so in a given mass, here's how much bluer AGNs are as they increase in luminosity. And the different color points are just a low redshift and a high redshift sample. They really show the same kind of trend. But there's really no trend with stellar mass. The AGN luminosity doesn't care at all about those galaxy stellar mass. Okay?
You're calling these things blue, but they're emission lines. So I don't quite understand what blue versus having emission lines and band passes mean. To me, blue means a blue continuum, which is fine. You also
Yes.
have emission lines, so
Yes.
you're mixing the two together here.
Yeah, well, let me think about how to answer this. This is a little tricky. Okay, so when a galaxy, this is a very good question. When a galaxy is blue, it means it had recent star formation. It's got O and B stars, which tend to have hotter blue and UV brightness. Okay, so when I'm looking at a color mass diagram, these things are blue, which means they had recent star formation. It doesn't necessarily mean they have instantaneous star formation, which is better tracked using emission lines, using H2 region gas. Okay, I'm selecting these AGNs based on broad emission lines. Again, typically, well, in this case, I'm actually using the broad H beta and broad H alpha emission lines, which are easy to distinguish from the narrow emission lines, which come from H2 regions. Okay, I mean, it's easy to distinguish them, but it's sort of hard to model and totally separate them. So it becomes difficult to measure the instantaneous star formation rate. To subtract away the broad line, take the narrow line, the narrow line that's left, and say, well, this is all star formation. That becomes difficult. A much better way to do this, sort of measure an instantaneous star formation rate, is using Herschel, using far infrared data. And they actually tend to find the same kind of thing. They tend to find that if instead of using sort of offsetting galaxy color, which I'm using as sort of a stand-in for star formation, if you instead turn this into a far infrared luminosity, okay, and you sort of invert the axes such that higher star formation rate is down here, redder, less star formation rate is up here, you see the same kind of trend using Herschel. So that's a better way to find the instantaneous star formation rate. I will show you one Herschel result. I haven't worked on Herschel, but I will show you someone else's result. Does that help? Okay, great. Okay, so this is where I think sort of normal bulk by number L-star kinds of AGNs lie. They tend to lie in star-forming galaxies. And the more star formation in the host, the more luminous the AGN, okay, on average. Well, what about the morphology of these systems? Well, one of the things we noticed in Cosmos out of redshift 2, and also, at Candles out of redshift 2, and also in Cosmos at redshift 1, was that AGN are frequently in disks in the high redshift universe. Okay? It actually turns out that when you look at redshift 0, this also tends to be true, so long as you are not biased to only high-mass AGNs. Now, if you look at a mass-matched control sample, again, of AGN, red points, and control galaxies, blue points, you see that, first of all, the AGN fraction is quite high, and it's about 50% of disk-dominated things. But I should say that AGN are slightly more bulge-like than mass-matched inactive galaxies. So AGN are very frequently in disks, even if they're more spheroidal than inactive galaxies of the same mass. Okay, so there are a lot of AGN in bulgeless disks, about 20% of redshift 2 in this particular sample with its particular selection limits. And they are a little bit more spheroidal, but lots of them don't have any kind of, some of them don't have any kind of bulge component, even though they are a little bit bulgier than their inactive counterparts. And it actually turns out that when you look at AGN luminosity with bulginess of the hosts, as you increase in AGN luminosity, you get more bulge. I'm not showing that here, but we address it in these papers. Okay, so AGN are frequently in disks, but as they get more luminous, they tend to be more and more likely to be in bulges. As we go down to very low mass AGNs, and looking for them in very low mass hosts, which is something that I've been really interested in. I'm going to go a little bit tangential, but this is still part of this idea of where do AGNs live. Again, we can use this nuclear versus extended emission line ratio selection, and we can find AGNs even in these tiny little things. I think these have bona fide AGNs. Their nuclear regions look AGN-like compared to their extended regions. I think the only plausible way to explain this is to have a weakly accreting AGN. These things you can see, as much as you can resolve their morphologies, they don't have a bulge component. Right? Certainly not a strong one. But they do tend in their stack data to have almost, when you bootstrap and you look at the distribution, almost all of them tend to have some kind of weakly accreting supermassive black hole. And so what I think that this is telling us is that, particularly at high redshift, we may be sort of answering the chicken or egg question. Do we have black holes before galaxy bulges? I think we do. I think we may be seeing supermassive black hole seeds from the early universe left over in these low mass disk galaxies that have not yet grown bulge. So I do think the AGN can come before the bulge. So that sort of returns to your question at the beginning. Okay, so let's summarize everything together into a sort of cartoon picture. Okay, there are some AGNs and mergers, but these tend to be highly luminous. They tend to be heavily obscure. Okay, if I make a cartoon diagram of accretion rate of the AGN, how much stuff is falling into the black hole, which of course tells you also how bright it is, with obscuration, all the way up here in the upper right-hand corner, this is where the mergers are. Okay, this is where the merger fueling of AGN is important. Okay? If I look at pretty rapidly accreting things that aren't obscured, these tend to be, I call this spheroids, but really I should just say bulgy. Okay, because they don't have to be pure spheroidal. They probably have a disk component, but they do have a bulge. Okay, these tend to be, they're observed as broadline AGNs, broadline Seyfarts. They tend to be massive, they tend to have massive bulges, I should say. So again, they have bulge components. I don't think there's a mass preference, so I should probably cross it out. But they are star forming. Okay, they go as star formation goes. As we get a lower accretion rate, we have disk-dominated things, even down to very low mass disk galaxies. And then eventually, I didn't really talk about these guys, but we have something called liners, where the emission lines are not really dominated by the supermassive black hole activity, but there is some X-ray emission. These are just red and dead spheroids. Okay, and they have a massive black hole relic, which is not accreting very much. So if you don't believe this result, where I just combined a whole bunch of different surveys of redshift 0, 1, and 2, here's the same result using just one survey, one selection method, X-ray selection, accounting for biases, trying to mass match. This is from Cosmos data. This is the same diagram where we see the amount of stuff falling into the supermassive black hole. We see the obscuration of that accretion. Okay, and again, we have obscured AGNs frequently lying in disturbed things. Okay, but not entirely always, but we do see sort of more disturbances as we move up and right in this diagram. Okay, these lines may be not totally correct, but you can sort of see a trend of more of these green points, which represent disturbed kind of merger systems. As we go to the upper right, higher accretion, higher obscuration. You see a lot of these blue things, particularly as you go towards the bottom left. Whereas up here, these things are spheroid dominated, even if I showed you that they are star formed. Okay, I should also say that this sort of dividing line, I like AGN. I like to think about what kind of physics is going on very near the black hole. And so I think as we are sort of lying above that dividing line, this is sort of the standard AGN model. We have this accretion disk. We have a corona, fuzzy corona above that, which is emitting all the X-rays. We have this broad line disk wind, which is causing the broad emission lines that we see. And we have a dusty torus forming at the end of this wave as it starts to bump up. As we go to lower accretion rate, we actually get radially inefficient in the central region. We call this a REAF, an 8F, whatever. The interesting thing here is that at high luminosities, we have this broadline disk wind. Okay, so we have a big quasar wind. At low luminosities, we have a stronger radial jet, okay, just because of the changing accretion physics getting near the black hole. So this becomes important in terms of AGN feedback. And I really want to encourage you, when you think about AGN feedback, what that might be doing to a galaxy, remember that there's two kinds. There's wind feedback, and there's jet feedback. Okay? And I'm going to come back to that idea. And this is sort of governed by the accretion rate onto the black hole, which is also governed by the host galaxy around that black hole, because I just showed you that. And here I'll show it to you again. Okay, so these things tend to be wind dominated, these things too, and these things tend to be jet dominated. Okay? So, let's go on to my last point. Okay, I think I'm doing well on time. Is there really coevolution? You know, I showed you the kind of hosts that prefer AGNs. Let's put this all together and try and talk about the physics going on here. Okay. Well, you know, I presented these theoretical models which say, oh yeah, there's lots of mergers make AGNs, that's how it works. Well, they make some AGNs, mergers do, but they all tend to be obscure type 2 quasars. And these things are very rare. They're less than 10% by number. I mean, they become like 0.01% if you include all supermassive black holes in the universe. Now, they are very luminous, okay? So they contribute a lot to the accretion rate of all, you know, if we take a supermassive black hole in the local universe and we say, how much of its mass was built in different phases, okay? Because this is a very luminous phase, you know, even though 0.1% of the time it was in this phase, it actually grew a lot while it was in the phase. But I still think this is less than 50% for a number of reasons. And I can actually tell you that Phil Hopkins has a paper in prep. So Phil Hopkins, of course, the big proponent of this merger model, is now starting to say, yeah, mergers are probably also less than 50%. He sort of revised his models and they come to that conclusion. Matching observations much better, as it turns out. Meanwhile, all these other kinds of processes, which I'm going to call secular, because they're not violent disk instabilities, they're not mergers, okay, they're just AGN growing, supermassive black holes growing alongside star formation, without any kind of violent non-secular process. You're, you know, violent and non-secular, I'm calling this the same thing. These are definitely the bulk by number, more than 90%, okay? And they're also probably more than half of a given black hole's growth over the cosmic time. Okay? So, you know, this right here would be coevolution, right? Mergers driving both, you know, with AGN. Well, I'll talk about AGN feedback in a moment. But these secular processes really aren't what I think is coevolution. I mean, you have, you know, the black hole growing alongside star formation, but they don't really know about one another. They just sort of happen to grow alongside each other at the same time. And I'll talk a little bit more about that. First, let's talk about quenching. Okay? So one of the issues, well, you'll recall that I told you that we see AGN alongside star formation. Okay, so if I make a curve, the cartoon model again. So if I make a curve showing what happens with the AGN, here we have the strong AGN phase, or the moderate AGN phase, weak AGN phase. Okay? These are the sort of host galaxies you tend to see alongside them in terms of star formation rate. Okay, you tend to see that star formation is highest in the strongest AGN phase, and as the AGN decreases, star formation rate decreases, the host galaxy gets redder. And you see the same thing with Herschel, okay, where you see instantaneous star formation decrease as the AGN decreases. So this doesn't really make sense for AGN quenching, because you would think that a strong AGN would be the things most effective at doing quenching. In these merger simulation models, it's the quasar wind, which I told you is associated with the strongest AGN, that is supposed to be causing the quenching. And we don't really see that. Instead, we see them sort of fade together in lockstep. Okay? We don't really see, you know, the star formation quench right with the strong AGN phase.
But doesn't the central torus obscure the wind, and so it can still have star formation in the disk?
Yes, exactly.
So it's not quenching the whole galaxy, it's only quenching the place that the...
Absolutely, absolutely. So if you recall back to the merger model that I showed you, Casey said, oh, is that wind actually spherical? You know, and you can see it extend over the whole galaxy. That doesn't work. You could, however, quench star formation very near the AGN. You could clear out gas. I think quasar winds are still important for metal transport, you know, but I don't think they're sweeping out all the gas in a galaxy and shutting off things in the disk.
You metal transport to the IGM or something.
Exactly, exactly. Yeah. And I do think radio mode feedback is still important, which I'll come to. So the scales of what we have going on here. You know, the torus through reverberation mapping, where we can actually directly measure its size using VGN variability, is a parsec, a couple of parsecs. So it's not as large as the whole bulge, right? So you're absolutely right, and you can certainly clear out star formation within a parsec, maybe even within 10 parsecs, but it's not clear that you do it to 100 parsecs. Certainly not to kiloparsec scales. And there are a number of papers claiming the sort of holy grail for AGN feedback, and I don't really believe any of them, because we have not seen a quasar wind at 1 parsec or 10 parsecs connecting all the way out to hundreds of kiloparsecs, or tens of kiloparsecs, I should say.
Right, that's what this model, you're saying basically it's only when there is broad line AGN phase that this wind's really active.
Yes,
An extension
exactly.
of the broad line region, basically.
Exactly, exactly.
Right.
Yeah, and we don't see quenching in broad light AGN.
Right.
We see them lie in highly star-forming galaxies.
Exactly.
So I would love for my AGN to be really important for galaxy evolution, but at least in terms of feedback, quasar feedback, they're not. I don't think that's what's going on. Instead, what I think is happening is the AGN is just going as star formation is going. And this is a paper by Jim Mullane, his sort of cartoon picture, and this comes a lot from, well, lots of observations, but he worked particularly on Herschel observations. Okay, so in his model, we have star formation represented here by M dot star. Okay, so galaxy growth just through star formation. Okay, and that's pretty smooth, but it bounces a little bit, depending on the small scale physics in the galaxy, maybe minor mergers, stuff like that. Okay? Meanwhile, the AGN is rapidly variable. We know this AGN vary a lot. And so the AGN has these sort of big spikes in accretion. Maybe a star falls in, maybe a gas cloud falls in. It's just totally random. Okay, all the gas that's falling into the AGN. We don't need tremendous torques from mergers or violent disk instabilities. It's just stochastic. It's just purely random. And the AGN may have spikes and vary a lot. But with time, as star formation increases, the black hole, or excuse me, the stellar mass of the galaxy slowly increases. The black hole may sort of look like this with little jumps, depending on these big accretion phases. And the ratio of black hole mass to stellar mass, this M sigma relation, if you will, it's mostly smooth. There's little jumps, but this is really just scattering relation. Okay. And averaged over large populations, we see a connection of AGN growth with star formation growth. Even if, at a snapshot in time, for an individual object, things may lie in unusual places, right? You may see lots of AGN activity with star formation. When we average lots of populations together, whether we do it in the SDSS, whether we do it at high redshift with Herschel, we see that the AGN just go as star formation goes, on average. Yeah?
So is that variation by a factor of 2 comparable to the scatter you see in the
That's
sigma
it.
relation?
It's
Because
not the
that's
scatter with M star. That's the only problem with this. It's scatter with the spheroid, not the stellar mass.
Yeah.
Right. Yeah.
That's a good point, right?
Well, so Alex Diamond-Stanek, a really close friend of mine from grad school, actually had a really nice paper where he said, well, hold on here. You guys at high redshift are all saying that the AGN is going as star formation because you're just measuring the number of star formation rate, because that's what you do at high redshift. But in the local universe, actually, it's that connection exists, but it's much more closely connected to star formation rate, nuclear, bulge star formation rate, if you will, within a kiloparsec. And that is actually a much better tracer. And actually, you may see star formation rate within bulge, spike a lot more closely as the AGN spikes. That may connect a lot more. This scatter probably decreases if this were bulge or sigma instead of total stellar mass. I'm not 100% sold on that because we do see, like I showed you, growing supermassive black holes in bulgeless disks. It's not really clear yet how common that is, if that's a redshift dependent thing. Also people argue for evolution in M sigma, such that at high redshift black hole M star may be a much better correlation. That probably doesn't evolve with redshift, even as M sigma does. So in other words,
That could make sense if this model's right.
yeah. So galaxies build up their bulge over time.
They build the mass and configure itself in a bulge, and then just one else coincidence with low redshift to see that fact.
Precisely. And this is another view of that coincidence. So you might be able to build in particular the black hole M star relation, but even the M sigma relation as galaxies build their bulge by coincidence. If you just start off with a sort of random distribution of C black holes. Now I will say that the normalization here does matter, okay, but the scatter does not at redshift 10. Well, not really. It can be huge scatter at redshift 10-ish, okay, and by redshift 0, you lie on this nice M sigma relation. And so there's no coevolution here. There's no feedback in this particular model by community. There's no feedback. There's mergers. There's stochastic growth.
Really just stick random black hole mass into
Random-
watch them
random-
merge and then love it.
Exactly. And they follow, I believe they follow merger trees from the Millennium simulation, something like this. And you just randomly reproduce this M sigma relation, just because. I mean, so they start with dark matter halos from Millennium, they turn that into stellar mass. They put random C black holes in them. And you know, galaxies have enough minor and major mergers from redshift 10 or 20 or whatever to 0, that you just stochastically get the M sigma relation. Okay. So there's black hole mergers, there's stochastic growth, which they do in a very, very simple analytical model.
You see black holes, they grow, I don't know if they grow with, I mean, like gas accretion or.
Yeah.
there's
Yeah.
some
So
model
they
for
go
how-
with gas density and say, well, some of that goes into black hole, some of that goes to star formation. But it's not self-regulated.
I'm sensing, I don't want to say kind of,
Yeah.
or interrupt too much, but I'm
Yeah.
sensing it's a sort of, Richard just means it's a I mean, if there's a lot of gas, it's going to fuel star formation, it's going to fuel black hole growth.
Yes.
They kind of track together that way.
Yeah, the fundamental
At least the
quantity
nuclear
here.
agents, right?
That's right. It may just be gas, and it does both. You know, and
Right.
you know, the M sigma relations are something like, you know, one black hole mass goes as 500, you know, solar masses in the bulge, right? So you don't need that much gas to fall into the black hole, right? And you can probably do this with stochastic methods. You probably don't need efficient angular momentum transport. You know, just a random disturbance can toss 1/500th as much, you know, of the gas into the black hole and grow the black hole.
So one of our faculty who's not here today, unfortunately, always likes to say when he looks at this plot, big things are big.
Yeah,
And so
yeah,
he'll
yeah.
be very proud. We'll tell him when he goes.
Yeah, and I think,
Plot anything in log log plot is a straight line.
well, that's true too. Yeah. So you know, in that respect, the M sigma M star relation, the pH M star relation, whatever, is a little bit misleading, you know. But on the other, the scatter becomes important, right? Because you can see lots of scatter at low masses and a little bit of scatter
Right,
at high masses.
that's a good point, because this model, you know, things that are 10 to the 7 to 8 should have very low mass black holes.
That's right. That's right. And we may be able to see some C black
And the
holes.
scatter should be enormous.
Exactly. As we go to higher redshift, as we go to extremely low masses, you know, and try and see these black hole relics. Yeah. And I think spatially resolved emission lines are a good way to do that. Okay, so here's sort of a wall of text, sort of summarizing everything I said. I think that the real summary is just that the black hole is probably just along for the ride. Okay, which is kind of disappointing to me, you know, because I want to convince you that what I do is really important. You know, that studying the small scale physics around the AGN matters. You know, it's going to change galaxies. It made the Milky Way what it is today.
But actually, you have it there, the rate, I mean, okay.
Yeah,
They're going to want to.
You know, and it is still important. Okay, I didn't talk at all about radium maintenance mode feedback because I was much more interested in quasar wind feedback. I sort of found that quasar wind feedback doesn't really happen. Well, I don't say that here, but no wind feedback. Probably you can still get efficient metal transport. You see this because AGN tend to be extremely metal enriched, even at redshift 6. And they do have winds, even though they don't blow out all the gas in the galaxy, they do extend to kiloparsec scales in small cones. So you might still get a lot of metals off the AGN, which then fountains back, you know, through this baryon cycle. Maintenance mode feedback is important. This is observed. We see this in cluster cores, where we know that we're reading cluster cores with radio mode feedback. It is not as clear if it works in elliptical galaxies to keep red galaxies red, keep galaxies quenched. I think it's probable because when we see a red galaxy, we see a liner, we see a weakly accreting AGN, which has a strong radio mode because of its accretion physics. So I think radio mode feedback is still important, even if quasar wind feedback is not. And I also think it is interesting to look for seed supermassive black holes from the early universe, particularly through looking at the scatter in the M sigma relations. And I think I will just leave you with this picture. I think secular fueling is what's going on. I think that's how AGNs grow alongside their hosts, how supermassive black holes grow alongside their hosts. So thanks.
Great, thanks, Tom. We had plenty of time for more questions, actually. Okay, Nick?
Yeah.
This diagram over here in the
Yeah.
lower right corner, you have high obscuration and low accretion rate.
Yeah.
Don't you have a selection bias against not finding objects?
Precisely.
And then the obscured types could just be filtering that have high accretion rates. You could be hiding a significant population.
You're absolutely right. So the reason I have nothing here is because I have not been able to find them. So you could potentially find, but yeah. So I think you can find these things. There was actually a paper by Neil Brandt's group, when I working with at Penn State, where they looked at the remaining unresolved X-ray sources after the deepest X-ray survey in the sky in good cell, 4 megaseconds, 4 million seconds, just a tremendous. Yeah, so that's, I mean, what, like a tenth of a year? Yeah, it's a month of Chandra just staring, of ridiculously expensive space telescope time, just staring. Anyway, so they looked at what was still unresolved, okay? And they sort of expected to see, some obscure things in high-mass galaxies, maybe, weakly accreting things at high mass. They didn't find that. They were pretty surprised. What they found was the same sort of thing I was finding. They found AGN tend to be in these low-mass disk galaxies, okay? So now when I use my spatially resolved emission line ratios, it's mostly insensitive to obscuration. It's certainly insensitive to torus obscuration. And it doesn't even really care that much about large-scale obscuration in the host. But I can't quantify that obscuration, right? I just know that there are weakly accreting AGNs there. When you use X-rays, particularly when you stack all the unresolved sources and you try and figure out where that's coming from, all the unresolved background, and you stack all these low-mass galaxies, it turns out that the X-rays are obscured. Okay, so these kinds of things, highly obscured, low accretion rate, are probably sitting in low-mass galaxies. They may actually be the same things as this, which is sort of why I put this in the middle. I'm not totally confident of that. But this sort of population may extend out here. And it may, I don't know why they'd be obscured. And I've chatted a lot about this with Neil, and he doesn't really know why either.
A lot of work done back in early Spitzer days. You're no longer obscured by the torus per se, but just that
Yes.
random inclination because you're looking through the galaxy, and so you get
Yeah.
that.
And these are disk-dominated
confidence.
things. We know from, say, Arne van der Waals' work that it's actually common for them to be tremendously starbursting. So they have a lot of gas. A lot of gas probably means a lot of dust. Yeah. I'd love to look at some of these things with Alma. It's going to take a while to be able to get that kind of all the time. But, yeah.
The same thing, what you were saying, is it the same thing as saying it's constrained from the X-ray background? I mean, the X-ray background must have some constraints on the number
Yes.
of these low luminosity
Yes,
things.
you're absolutely right. I said that good south, this particularly deep region, has 4 million seconds. Neil actually has 3 million more coming this spring, and he still wants to push to 10 million seconds. Chandra tends to be background limited,
Right.
such that when you see an X-ray photon, it really is coming from a source.
Every photon is sacred.
Exactly. It's not like HST or anything in the optical or anything in the infrared, right? Where photons are mostly coming from sky, or even in space they're coming from, dust, whatever. Some sky, even on your Hubble is.
10 million seconds is a third of a year.
Yeah.
So even if the source is one photon,
Yeah.
a third of a year.
Yeah. But this also, going from 4 to 10 helps you a lot stacking the unresolved sources that still remain and constraining how obscured are they? Can we actually detect around K alpha, which tells us a lot more about their obscuration properties? Are they cotton thick? I think that's going to be exciting. I'm sort of embarrassed about it because it's such a ridiculous amount of telescope time. But
Every telescope should spend much time in good stuff, but that's a different
yeah,
story.
I agree. Yeah,
Before we digress anymore, then we're pushing.
yeah.
Well, John is around all day today. He's
Yeah.
around tomorrow morning. And we take him lunch and dinner. I think we scheduled grad student harassment at 2. So I'll come find people and beat the drums for that. So, otherwise, let's thank him again.